Hello friends, in this video we'll discuss about the operators, the second part. Already in the first part we have discussed what is operator, linear operator. We have discussed about commutative algebra, Hermitian operator, eigenvalue function. These things we have already discussed in the first part. The second part will discuss the remaining four things, that is what is orthonormal conditions, okay, and we'll discuss about average value of an physical observable of a system, and we'll discuss about ladder operator, what is ladder operator, and we'll discuss about equation of motion. And the last will derive some operators of some physical quantity, physical observable. Okay, these things we'll discuss in this video. So let us start with our topic. First discuss with the first topic, that is orthonormal condition. Before going to discuss this question, we should know two conditions, two concepts. Two concepts are, first one is what is orthogonality of functions, of wave functions, and normalization of wave function. These two things we should know before going to the orthonormal conditions. Okay, so coming to the first point, orthogonality. So what is orthogonality? Suppose you have two wave functions, psi1 and psi2. These two wave functions are said to be orthogonal to each other if it satisfies these two conditions. That is, if integration over psi1 star, that is the complex conjugate of psi1, and psi2 d tau equal to 0 and psi2 star psi1 d tau equal to 0, if these two conditions are satisfied, then psi1 and psi2, these two wave functions are said to be orthogonal to each other. Again, if we see the normalization of a wave function, then we see psi1, this is a wave function, is said to be normalized when integration over psi1 star, that is the complex conjugate of psi1 and psi1 d tau equal to 1. Similarly, psi2 is also said to be normalized when it satisfies psi2 star psi2 d tau equal to 1. This condition is satisfied. When both these conditions, when a set of wave functions, that is psi1 and psi2, these two wave functions satisfies both the 1 and 2 conditions, that is the orthogonality condition and normalization conditions, then such wave functions are called as orthonormal wave functions. Okay, we will solve problem from this part later on from the previous year question paper. So now we'll discuss the second point. What is this about? Average value of a physical property. So now we'll discuss about average value of a physical property. We know that in quantum mechanics, every quantum mechanical system has some property, physical property. Okay, these are physical property, and this physical property corresponds to an operator A cap. Okay, and the average value of this physical property, which is denoted by this, is given by the expression psi star, where psi is the wave function of the quantum mechanical system, A cap psi d tau divided by psi star psi d tau. When this wave function is normalized, then we have what we'll have, this term goes to equal to 1, then A cap will be the average value of the physical property will be psi star A cap data. Okay, this is the true expression of average value of a physical property in quantum mechanics. Now we'll see ladder operator. This operator also called increasing order operator, also called as increasing operator or decreasing operator. This is because this operator has an application on any kind of operator acting on any kind of, when we apply this concept, the eigenvalue of an operator, the eigenvalue of any operator may be increase or decrease when we apply this concept, ladder operator concept. This ladder operator concept find an application in the harmonic oscillator, quantum mechanical treatment of harmonic oscillator, and angular momentum. Okay, in these two fields, this ladder operator has its application. So we'll see on angular momentum. Suppose angular momentum of a system is given by L. Okay, this is the angular momentum, and it has three Cartesian coordinate Lx, Ly, and Lz. Okay, then for this the two ladder operator will be given as L plus, where L plus is given by Lx plus I into Ly, and L minus L negative Lx minus ILy, where I is the imaginary component of ladder operator. So these two are ladder operator. We'll have some property between this component and the ladder operator. These property are basically commutative property, and these are as follows, and you should remember this property. Commutator of this two-letter operator is equal to twice of H cross L of Z, and commutator of the positive letter operator and L of Z, that is angular momentum Z component, is equal to H cross L of positive. Again, the negative letter operator and L of Z equal to minus of H cross L of minus. Okay, and commutator of these two components is equal to Z and Y is equal to I H cross Lx, and commutator of Lz, that is the component of angular momentum and component of the position vector Y, is equal to I H cross x, this is the position vector, and Lz and Z, this commutator is equal to 0. These three property you should know, because question directly asks from this property. Okay, from letter operator part, this is all about from letter operator part. And next we'll discuss about equation of motion. This is the number 4 part, the equation of this equation of motion is nothing but, we know in quantum mechanics, in quantum mechanical system, the average value of any physical observable has some dependence on time. This dependence on time is expressed in terms of, is known as equation of motion. It is a long derivation to derive this equation, but we only follow this equation only for sake of our interest to solve problems. And this equation is given by I H cross average value of the commutator A cap and H cap. This is the Hamiltonian operator of the system, and average value of dA cap by dt. This is the main equation. Okay, this is the main equation of motion. But in this case, this operator directly does not depend upon this time. So this term will equal to 0. So we will have only this equation. Okay, if this term is equal to 0, if this is equal to 0, then dA cap dt equal to 0, that is the average value is a constant value. Okay, this is the equation of motion. Question asks from this equation of motion directly. It always asks when it is constant. Now we'll derive some operator of physical quantity of quantum mechanical system. derivation of operators. According to the third postulate of quantum mechanics, we already said that in quantum mechanics, the Cartesian coordinate of the classical mechanics is replaced by x, y, and z. Okay, and the linear momentum is given by these two values. Okay, in order to find out any operators in quantum mechanics, we should put these three values of xyz by xyz and the linear momentum px, py, pz by these three values. Okay, so let's find out the operator for linear momentum. Okay, linear momentum is given by px, py, pz. Okay, so these three are unit vector along xyz. So we can write this will common out as all the three terms have the same quantity dx I cap dd of y j cap and dd of z k cap. So this is the operator for linear momentum. Similarly for kinetic energy, half of m vx square, which is equal to mvx whole square divided by m, which is equal to px square divided by twice of m. We can replace this px value equal to this value minus of half of twice of m minus of I is cross divided by dd of x whole to the power square. Okay, which will be equal to I square h cross square d square divided by dx square. This will be equal to minus of twice of m I square equal to minus 1, this minus h cross square d square divided by dx square. So this is the operator for kinetic energy. So now we'll see the operator for potential energy. For potential energy, we know that for potential energy V x, y, z in terms of these three coordinates, generally potential energies are expressed. Therefore, the operator is also expressed in these three Cartesian coordinates for potential energy. Okay, for potential energy. Now we'll see the total energy operator. That is the kinetic energy and potential. This is equal to the h cross square divided by twice of m d square dx square d square divided by dy square, d square divided by dz square for 3-dimensional system, and v is replaced by v x y z is a function of these 3 coordinates. Okay, so this term can be written as delta square h cross square by twice of m by delta square v operator x y z. This is the total energy operator. This total energy operator also known as Hamiltonian operator. Okay, so this is it from the theory part of operators. The next video will discuss about some problems from the previous year question paper and the other questions as well. Thank you guys.
So guys, if you have any doubt, please let me know in the comment section below, and subscribe our channels for more videos on chemistry based on CSIR net and GATE as well, and press the bell icon for instant notification. Thank you.